Very early in the course, we learned about how to solve n linear equations in n variables, and that's the matrix vector system AX equals B. Now, most recently, we've been looking at solving one nonlinear equation in just one variable, so the scalar problem of finding a root of a function f. We're ready now to talk about having nonlinear equations in multiple variables. So n equations in n variables, we'll just write that as f of x equals 0. And this problem generalizes both of the other two. So when we talked about linear problems, we had to deal with multiple dimensions. When we talked about scalar root finding, we had to deal with nonlinearity. So now we're going to put those two things together. We're going to have multi-dimensions and nonlinearity at the same time. Okay, so as an example of this kind of problem, this comes up in steady-state dynamics of dynamical systems. So here's an example that comes from biology. There's a very famous type of model known as SIR. S stands for susceptible individuals, I stands for infected individuals, and R stands for recovered individuals. And so here are some simple ordinary differential equations. So imagine that these populations are all functions of time. So we can write down a model that describes the evolution of these three populations in terms of some differential equations. So there's a differential equation for S, an equation for I, and an equation for R. So together these make up a dynamical system. So here the variable x is a function of time. It's a vector consisting of the three population values. F then is a map from the three values of S, I, and R into the three values of ds dt, di dt, and dr dt. So we might write this mathematically as f of t at each time. I'm sorry, f is not a function of time. So f itself is just a map from n variables to n variables. Or n variables to n values, I should say, not to variables. Okay, and then whenever we have a dynamical system of this form, one of the first things you often want to know is, are there any steady states? So a steady state is where things aren't changing. Okay, if things aren't changing, that means the derivatives are 0. So if we want to find a steady state of this dynamical system, we set f of x equal to 0. Any solutions of that nonlinear system of equations is 0. I should just point out the equations are truly nonlinear, so each variable independently, the s, the I, and the r, each one on its own does appear linearly, but when you have the product of two variables, those are nonlinear interactions. All right, now we have the solution of a fixed point iteration for a root finding problem in one dimension. We can actually generalize that to multiple dimensions very, very easily. So let's suppose we are given a function f of x. Here again, f is a map from n dimensions to n dimensions. And given that f, we can define a g, which is just the difference between x and f of x. So x is an n vector, f of x is an n vector, so g is also a map from n dimensions to n dimensions. And furthermore, the algebra is very simple. If f of r is equal to 0, then g of r is equal to r, and vice versa. So a root of f is the same as a fixed point of g. So with that in mind, it's very easy to generalize our fixed point iteration. We would just define xn plus 1 as g of xn. And since we have a formula for g, we could write it in terms of the original f instead. So this gives us an iteration, right? N is equal to 0, 1, 2, and so on. The starting value x0 is given. So given x0, that's a starting vector. Then we plug in n equals 0, and that tells us how to find x1, another vector. And then we use x1 to find x2, and so on. Now when we did this for the scalar fixed point iteration, we found that the error is multiplied from one step to the next by g prime of r. And so we wanted the absolute value of g prime of r to be less than 1 in order to get convergence. Well, what is that going to mean here? Because in that problem, g was a scalar function of one variable, so we just took its derivative. We know what that means. But we're going to have to talk about what that means in the multidimensional case, generalize the idea of a derivative to multiple variables.